chapter 9 today, which builds on things. Uh, e- each new thing we have is building on something. But the last several tests we've had have all been about what if I have this quantitative variable I want to test information about. But way back in chapter 1, chapter 2, we talked about there's two different types of data. There's the quantitative things that can be that makes sense to take a mean, that makes sense to add together, makes sense to use arithmetic operations on. And then there's the categorical, the stuff where that doesn't make sense. The things where it's these people or these objects fall into one of several different categories. So we had two-way tables. And I remember several different problems you had through there. One specifically coming to mind was there was a Titanic problem of looking at the survivors versus what class, things like that. We looked at these two-way tables, but we haven't had a test about this yet. That is what chapter 9 is all about, is if I have two categorical variables, can I see if there is a relationship between them? A relationship exists when that distribution of one variable depends on the value of the other variable. And so when data are obtained from random samplings, two-way tables of counts can be used to formally test the hypothesis that two categorical variables are independent in the population from which they were obtained. So we'll see a little bit more of that, but seeing that the population they come from doesn't affect their distribution. So when that's the case, when that's the thing we're looking for, our null hypothesis is generally the two variables that we're looking at are independent in the population. And then the alternative would be they're not independent in their population. There is a different situation in which the chi-square test may be used. Suppose we have C independent random samples from C different populations, and we classify the individuals within the sample according to those categorical variables that take on our values. So we split up all of our individuals into the two different categories of, like the example given, we split them up based on I think it was survival and class for the Titanic example. Each person fell into one of those categories. And then the chi-square test, or the test that we're going to be doing, has the null hypothesis that the distribution of the categorical variables is the same in each of the C populations. Ultimately, these two null hypotheses are generally ultimately saying the same thing. Of if I'm looking at two different columns, say in the Titanic survived versus not survived, the chi-square test would be testing whether or not that class actually had anything to do with it on a more formalized level than just looking at numbers and being like, oh, it looks like these numbers say there's an effect. Chi-square test is formalizing that did the class actually have an effect on whether they survived or did not survive? Were they independent from each other in the population? Are the distributions the same in each of those C populations? So to test this hypothesis, we compare actual counts from the data compared with expected counts, where the expected counts are what are expected when there is no relationship. The expected count in any cell of the two-way table, we calculate by taking how many are in a given row. So the full row together, the full set of first class passengers, times the column total. So in this example, if I want to know the expected count of first class passengers who survived, I would take all my first class passengers total times everyone who survived total and divide that by how many people in what we're looking at. So expected count equals row total times column total divided by n. What the chi-square test is doing is our two-way table has the actual data in it. It has the actual what happened. Then we can calculate this expected count, and the chi-square test is comparing how well does what actually happen compare with what is expected to happen based on our total numbers. And so to see whether the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the counts that we would expect if the null hypothesis were true.
You go to the top second. Thank you. Appreciate it. I'll take a picture of it. Thank you.
So we're seeing whether this data gives convincing evidence against the null hypothesis. We're comparing that what actually happens in our sample versus what we are expecting to happen based on our row and column totals. So assuming there are R rows and C columns in a two-way table, this means there are R times C cells. And that's gonna be important in that for the chi-square test, there's gonna be a degrees of freedom as well. The degrees of freedom are going to be my number of rows minus 1 times my number of columns minus 1. So the test statistic that makes this comparison about how does the expected count compare with the actual count is known as the chi-square statistic. And the chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula is going to be we take the observed minus the expected for every cell, how far away they are, and we add this distance component that's pretty typical of squaring it. And then we scale it based on what we expect. So observed minus expected squared divided by expected. And each one of the cells in our two-way table, so I keep using the Titanic example, but just to remind ourselves, the two-way table had a column variable. In our Titanic example, I think it was survived or didn't survive. And then it had row variables. In the Titanic example was class, so like first class, second class, and third class. Each one of these has an actual what happened versus an expected. So each one of these cells has this observed minus expected divided by expected. The chi-square statistic is doing this calculation for every single cell and adding them up together. So one last thing is we're going to add them all together for every cell. So the sum of the observed minus expected squared over expected is that chi-squared statistic, where that observed represents the observed cell count of what actually happened in the sample. Expected is the calculation we have for expected, row total times column total divided by n. And the sum is over all of our cells in our table. This creates a distribution, and note, I noticed early this morning, too late to do anything about it. Everywhere there's a c squared, that's supposed to be a chi-squared. It's all the Greek got changed here. So these should be chi-squared. When the observed counts are very different than the expected counts, well, if observed is very different than expected, that's going to be a large amount squared and then scaled. When they are very different, we're going to get a large cell count, and then those cell counts add up, providing evidence against the null hypothesis, saying, we first said, hey, our null hypothesis is that in the Titanic example, whether they were first class or second class or third class didn't affect whether they survived or didn't survive. If the counts are much different than what is expected, this is evidence against our null hypothesis. So when the observed expected counts are in close agreement, the observed minus expected is really small. A small value of chi-squared root was up, and then the p-value for the chi-squared statistic comes from comparing the value of the chi-squared with critical values for this chi-square distribution. And so like the t-distribution, for every degree of freedom, we get a slightly different shape of a curve, but still has that peak shape. And what we are ultimately finding is the area to the right of that chi-squared value. And that area tells us our p-value when we're comparing things. So quick summary before an example. The chi-square test can be used when we're trying to see if simple random samples are independent within their two or more populations, or if I take a single random sample with each individual classified according to both of the two categorical variables. In either case, we want the expected cell counts to be at least 5. All individual cell counts should be at least 1. So these are each individual observed cell count should be at least 1. And in a 2x2 table, all 4 expected cell counts should be at least 5. These are those similar conditions to in our proportions, we needed at least 10 successes and 10 failures. In using any of the normal distributions, we needed the population to be approximately normal and for there to be a simple random sample and independence. Those are essentially our conditions that we're needing to check off. And so our steps for running a chi-square test, type, it's going to be a little bit faster. Step 1 goes back to chapter 2. The thing we did in chapter 2 is step 1, is calculating descriptive statistics that convey some important information about the two populations. This is usually column or row percentages. Again, these were what you were generally asked to do in your chapter 2 homework items of calculate the descriptive statistics for, I think another one you had would have been sleep versus stress levels. Calculating those descriptive statistics to see, hey, does this distribution seem to be about even? Generally that first idea. Then, step 2, find the expected counts and compute the chi-square statistic. So each cell has an expected count. So then each cell has the observed minus expected squared over expected. Three, compare the chi-square statistic to the critical values for the chi-square test. There is another table that is entirely for the chi-square test. And we will look at it. It's table F. This is the step of find the p-value. After we find a p-value for everything else, what do we do once we find the p-value? I know my p-value is 0.018.
Reject or fail to reject.
Yeah, I make a conclusion. I reject or I fail to reject, I make a conclusion. Same thing. We're going to draw a conclusion about the association. Similar in our similar to making a conclusion every other time we've done. Here's a p-value. We compare it against a significance level. We either reject or we fail to reject. And then also what that means in context. This is where a little bit more of that in context is greatly important because the null hypothesis is phrased in a slightly more obscure way. It's not necessarily immediate what the conclusion then means. So saying what we're saying in context is a little bit more important. So looking at an example, we have some stores trying to get people to buy wine based on music being played. And they want to see if the music being played affects the purchases these people make. The supermarket randomly assigned treatments, no music, French accordion music, or Italian string music. Under each condition, the researchers were recording who bought what. And so we get a table based on these items. So, one, calculating the conditional distribution is that chapter 2 idea where the conditional distribution for the type of wine sold under each treatment would mean I want to know if specifically, if no music is playing, what proportion of French wine was bought. If no music was playing, what proportion of Italian wine was bought? So how would, numbers wise, how would I calculate that for no music versus French wine? I wanted to know what proportion of French wine is purchased when no music is playing. How do I calculate that?
30/84.
Yeah, 30/84. That calculates out to be 0.35. Looking at a different one to ask the same question. If Italian music is playing and I want to know about other wine being purchased, how would I find the proportion of other wine being purchased when Italian music is playing? Yeah.
You take the 35 divided by 84 again.
Yeah. 84 again, more because these have the same total at the bottom. 35/84 comes out to be, assuming I did all my calculations correctly the first time, 0.416. And filling in some of these others. We would do the same calculation for each one. So Italian wine with no music playing would be 11/84 or 0.13. I'm gonna just fill these in. I'll do it for the Italian wine and French music. Italian wine and French music. This one has a different total. Only one person purchased Italian wine, or one bottle was purchased. Out of 75 total being purchased. So that 1 divided by 75 gives us 0.013. And again, in chapter 2, concepts. If I add up everything in my column, there's some rounding errors, but basically, what do the proportions of these columns add up to? 1, because we're finding the proportion out of the treatment. So these, again, there's a few rounding errors, but in general, they add up to 1. And then with the chapter 2 ideas, we often then looked at this and said, like, what general types of conclusions are we seeing? And by and large, it does seem like there's a degree to which it's being affected, especially when we look at this French versus Italian there. We have some counter ideas happening. looking at all the others, not a ton of difference. Is across the board, Italian just being purchased less. So the distributions, you can see some with our numbers where it seems like music is affecting the purchases. And in other ways, if I look at Italian across the board, being purchased less, French being purchased more. Across the board, there might not be a whole lot in that distribution difference. The next page has the actual breakdown with graphs. Pointing that out a little bit stronger. Again, like I said, Italian wine, the board is our lowest. What was the other one I said? But the distribution still seems to be approximately the same across the music. Kind of similar shapes going on. The chi-square test helps us actually determine what is happening here more than just our eyes visually can see. So now let's actually run our chi-square test. We need to calculate expected counts. Have the important information here. Gave the formula. How do I find expected counts? How do we find expected counts? Row total times column total over n. In this case, first of all, what is n? N is going to be the same for everything. 243. So if I wanted to fill in the French wine no music cell, my row total is the 99. My column total is the 84. So I'd have 99 times 84 divided by 243. Somebody with a calculator, what does that come out to be?
$308 over 9 or 34.2 repeat.
So we expect if the distributions were to be the same, exactly the same for each treatment, each type of music, we would expect about 34.22 bottles to be sold. Something to note, notice the column total is the same in both of these columns, which means when I do row times column divided by 243, this cell is going to be the same as that one. It's still going to be 99 times 84 over 243. So this is going to be 34.22. How would I calculate the French music one? The one in the middle there that I skipped over.
75 times 99.
Yeah. Row times column over 243. And should be 30.55. Fill in the rest for us because it's that same process over and over. Take row times column divided by 243. 31 times 75 over 243 should be 9.567. The no music column and the Italian music column are the same because the column totals are the same. Can somebody fill in that last one for, or tell me what that last number is going to be?
$34.88.
34.88. 75 times 113 divided by 243. These are what we would expect if all we knew was, hey, when No Music was playing, 84 total bottles of wine were sold. And when if all we knew was in total we had 99 bottles of wine. Fresh wine purchased. If all I knew was my totals, these are what I would expect if the distribution was the same. The chi-square calculation, then for each item, each cell has its own. So for an individual cell, how do I calculate that chi-square statistic? So I'm saying without the sum portion. You have a formula for that one as well.
Observed minus expected squared over expected.
Yeah, observed minus expected squared over expected. So our observed French wine with no music was the 34.22. How many observed was it actually? What was the number?
0.35.
That was the proportion.
Sorry.
Was the actual number.
30.
Yeah, from our original table, we have 30. Oh, eraser. So we have 30 minus 34.22 squared over 34.22. Somebody with the calculator again. What does that work out to be?
$0.520.
0.52. Relatively small number. But actually comparing it requires going to that table. But once again, this is just for one cell. To do the full chi-square statistic, we have to do all 9 of these cells and add them together. One of those, the calculations themselves are not that hard, but the process is pretty long. So a lot of times problems will break down to find it for just one cell or find the chi-square statistic for just one column. That is trying to take out how long of a process it's going to be. Just you can do it for one cell. No, near do this whole process for everything else. I will say for your post-class activity, there is one of do it for just this one cell. Find the chi-square statistic for blah cell. But then to actually find the full thing, we would find this observed minus expected squared over expected for every cell and add them together. So we'd have that process 9 times. So find all 9 and sum together. And when we find all 9 and sum them together, we ultimately end up, it's said on the next page, with chi-squared is 18.28. Here we have our null and alternative hypothesis. The null hypothesis would ultimately be that the type of music playing is not affecting what's being purchased. You can play whatever music and the same distribution will happen. The alternative is that there is a difference. There is some difference in these distributions that different wine is purchased when different music is playing. So we have our chi-square statistic. Our statistic is not our p-value. Just like with all of our other tests, our statistic tells us where we're looking on our table. It does not tell us our actual p-value right off the bat. So this is one where, again, we needed degrees of freedom. I have the formula there. We used row R and C before. Here it uses K and N. But either way, it's the rows minus 1, number of rows minus 1, times number of columns minus 1. So how many rows were there in our table? How many different things were we looking at being purchased? 3. And how many different treatments were there? 3. So we had a 3 by 3 table. So our degrees of freedom will be 2 by 2 or 4. Right. I did not get table F up readily enough. So let me pull that up. Yeah. We have our tables in the back again. They load. This time we want table F, and it actually says the chi-square distribution critical values. What was our degrees of freedom? 4. What was our chi-square statistic? 18 something. So specifically, because I do see 18 is on here, or an 18 point something is on here, 18.28. And this is like how we would use it for the T distribution, where go to our degrees of freedom and look for where would 18.28 fall. Fall somewhere down here. 18.28 would fall. These numbers are 16.42 and 18.47. Our statistic falls between 16.2 and 18.47. So 18.82 is between 18.47 and 16.42.
You mean 18.28?
Yes, I do. If I can switch to eraser. I mean the thing that we actually had to it. Okay. And then what the top row tells us is what p-value relates to these. So 16.42 and 18.47. Let me scroll just a little bit so I can point at them a little bit easier. If I take this 16.42 and follow it up to the top, 16.42 goes with a p-value of 0.0025. 18.47 goes with a p-value of 0.001. So this tells me, going to the top, my p-value is somewhere between 0.0025 and 0.001. It could be 0.0028. Could be, sorry, it can't be that. It could be 0.0023. It could be 0.0018. As long as it's between that 0.001 and 0.0025, or we know it's somewhere in there. It has a concrete number. It is. All the table tells us is it's somewhere in there. If we compare against our typical significance level, is our p-value bigger or smaller than our typical significance level? Smaller. Both 0.0025 and 0.001 are both smaller than 0.05. So small p-value. What do we do with our null hypothesis? Reject. There's not a lot of evidence to support this. The null hypothesis claim. So we reject H naught. And what was said? Small v p-value gives convincing evidence to reject our null hypothesis. So in our context, we're done with our table. Pull that up. In our context of our problem, what can we then conclude? Music makes a difference. There is a difference in those distributions. If you were somebody running the supermarket wanting people to buy more stuff, you would want to be knowing that the music you're playing is making a difference. So there is a difference in the distribution. Depending on the music played. Music makes a difference. And this is where that first piece we did comes back. We now have music makes a difference. That first piece where we've calculated our proportions, and we also looked at this, would give us more of that idea of how does it make a difference. We would then, if we were the ones running the supermarket, we could then look at these pieces to start trying to see, hey, what should I be playing for what I want for for selling more to the people that come into my store. All right. So there is this version, and we're going to skip the practice for now. We might come back and do that. But 9.2 says there's another way we can use this chi-square test, and it's ultimately the same process. What really changes is the null hypothesis, and kind of, and what really changes is the degrees of freedom. But ultimately, same large overarching process applies. So we're starting with an example instead this time. Mars Inc. makes M&Ms. And their consumer affairs department has made a claim about the distribution of M&M's candies. And it says, on average, the new mix of colors of M&M's milk chocolates are 13% browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. The one-way table below summarizes. Somebody opens up a bag of M&Ms, dumps it out. There were 60 M&Ms in the bag, and they counted up and got 9 blue, 8 orange, 12 green, 15 yellow, 10 red, 6 brown. And they want to know, hey, does this match with what Mars is telling us the distribution should be? Does my one bag of 60 M&Ms give evidence to say, hey, this claim might not be accurate? So, because the company claims that 24% of all M&Ms are blue, we might believe something fishy is going on because 24% of 60 should be around 15, 14 to 15. And we didn't get 14 to 15 blue M&Ms, we got 9. So we might be thinking something fishy is going on. And so we could be using some past information and say, I want to test the proportion that 24% of M&Ms are blue, with the alternative hypothesis that's wrong. That 24% it is not 24% that are blue, where P is the true proportion of blue M&Ms. So we could use that past breakdown and use a past z-test or t-test, or this is a proportion, so z-test. And we could perform additional significance tests for each one. But when we're doing a bunch of separate significance tests, one can generally expect to catch something when something's not there. We'd really like to be able to do a test that tests everything all at once. So, and however, performing a one sample z-test for each proportion would be inefficient and lead to the problem of multiple comparisons. Talked about in chapter 5, we don't want to compare multiple times because there leads to the problem of we will catch something even if something's not there. So we would need to adjust for that fact. It gets convoluted. It gets complicated. More importantly, performing a one sample z-test for each color would not tell us how likely it is to get a random sample of 60 colors. That differs as much as the one claimed by the company. Multiple one sample z-tests are not going to take all colors into account at once. They are just going to take into account, hey, the blues were off, or hey, the greens were off. We want to be able to test all of our colors at once to say, is the company's claim accurate? Big picture. So that means we need that new kind of significance test, which is called the chi-squared goodness of fit. It is the chi-squared test But what it's ultimately for is when there's just one categorical variable. More importantly, performing one sample z-test for each that got copied and pasted. Yep, that just straight up got copied and pasted. Sorry about that. The hypothesis in the goodness of fit test then becomes our null hypothesis is what the company claimed. So the probability of blue is 0.24. The probability of orange is that there's 20% or 0.2. The probability of green is 0.16. The probability of yellow is 0.14. What did the company claim we would get for red on the first page? What proportion are supposed to be red? 13%. And that is the same for the brown. The z-test, what the point trying to draw home is the z-test would just test one of these. This goodness of fit is testing all of them at once of saying, hey, this distribution is likely or this distribution is not likely. And so the alternative would just be that at least one of these proportions is different than claimed. Just like with a regular chi-square test, we're going to compare the observed counts with what we would expect if H0 were true. The more observed counts differ from the expected counts, the more evidence there is for that null hypothesis. The more gets added to the chi-square statistic, the more evidence against our null hypothesis. What also is different here is a little bit of our expected calculation. Because our expected calculation is not just going to straight up be row divided by column total, because our column total isn't very helpful. We don't have multiple columns to add up together, right? So there's not really a row times column total we could do here in a beneficial way. But what we do have for our expected counts is what Mars says. Mars tells us what we should be expecting. If I open a bag of M&Ms, I should be expecting 24% of them to be blue. If I open a bag of M&Ms, I should be expecting 13% of them to be brown. So, in our case, assuming what Mars says is true, if I open a bag of 60 M&Ms, how would I find how many I would expect to be blue?
0.24 times 60.
0.24 times 60. So if we randomly sample 60 M&Ms, 60 candies, then 60 times 0.24 are expected to be blue. 60 times 0.24, I gave a range for this. I said that's somewhere between 14 and 15. It's 14.4 precisely, yes. So I would expect somewhere between 14 and 15, 14.4 of them to be blue. So we can do the same idea of with my observe, I can find my expected with 60 times 0.24, which was 14.4. Orange. What percent do we expect to be orange? Should be now written twice.
Right. 20%.
20%? Yeah, so 60 times 0.2. What is 1/5 of 60? 12. We expect 12 of my 60 M&Ms to be orange. And we can, again, proceed down. I know red, I will write out red and blue, red and brown because I remember that one. That's 0.13%. Or proportion. 60 times 0.13 is 7.8, and the reds and the browns were supposed to be the same. And each one of these, Mars has a proportion that they say to expect. So we can get how many of the M&Ms do we expect to be that color in a bag of 60. How do I find the chi-squared statistic? Like specifically if I wanted to do it for blue. Yep, 9 minus 14.4 squared over 14.4. My chi-squared statistic is going to be doing that for each one of these. So here is short enough. I'm actually going to write them all out. So then orange, the chi-squared statistic proportion for orange, that portion for orange, would be 8 minus 12 squared over 14, not 14.4, over 12. Green would be 12 minus 9.6 squared over 9.6. What would be yellows? I just heard the 8.4. I mean the whole fraction. Not 15. Yeah, these numbers keep matching. And there's something missing. Okay. Writing out two more of them. Red is going to be 10 minus 7.8 squared over 7.8. And brown will be 6 minus 7.8 over 7.8. What I want next is I'll be asking for a few of the different decimals of an individual fraction. So like what is 9 minus 14.4 squared over 14.4? 2.025. What is 8 minus 12 squared divided by 12? One point three three three. 12 minus 9.6 squared over 9.6 is 0.600. 15 minus 8.4 over 8.4 squared, 15 minus 8.4 squared over 8.4 should be 5.186. 0.6, 10 minus 7.8 squared over 7.8 is 0.621. 6 minus 7.8 squared over 7.8 is 0.415. Adding these all up, we should get 10.180. Here, the degrees of freedom change because, remember, it was number of rows minus 1 times number of columns minus 1. In the goodness of fit, there's only one column. Only one row. And if I took my one row minus 1, I get 0. So we ignore that part in the goodness of fit, and it's just number of columns minus 1. So how many columns when expressed this way? How many different colors are there?
6.
So the degrees of freedom would be we always subtract 1. So 6 minus 1, 5. It's just we don't subtract 1 from the number of rows because that would be 0. And we don't want to multiply by the 0. Oh, all right. So degrees of freedom is 5. Our chi-square statistic is 10.180. Using our table version, they've switched sides. Degrees of freedom, 5. So we're looking at that white column right above the blue, white row right above the blue. And I'm looking for 10.18. As I go across, 10.18 falls between 9.24 and 11.07. That's not what I want. I want to be able to. 10.18 in that 5th row is between 11.07 and 9.24. Going to the top, 11.07 goes with a tail area of 0.05. And 9.24 goes with a tail area of 0.1. If we use the significance level of 0.05, is our p-value bigger or smaller than 0.05? This is a nice one where it's written right there. P-value is bigger than 0.05. So when our p-value is bigger than our significance level, do we reject or fail to reject? We fail to reject. It's our just make this bigger again. Okay. Our null hypothesis is not really phrased in a way to quickly say what that means overall, but ultimately, what does failing to reject mean about Mars's claim?
It means we just like can't tell if it's true.
We can't tell if it's true. We don't have enough evidence to say my 60 M&Ms point to this being false. My 60 M&Ms that Mars's claim could still be true. We don't have enough evidence to say that the distribution is different. So, fail to reject H naught. We don't have enough evidence to conclude the company's color claim, Mars's color claim, is wrong. So the last page, I'll scroll down, talk about that a little bit. The last page is that big, just overarching what we do with the goodness of fit. But we've walked through that whole process. A categorical variable that has k possible outcomes with different proportions for each of our outcomes. We can test the null hypothesis that P1, P2, all the way through Pk are certain proportions. And then we can find that expected count based on whatever the claim is about this thing. And then calculate the chi-square statistic, observed minus expected squared over expected, and sum that over all k items. And then the p-value is the area to the right of that chi-square distribution on the chi-square distribution curve. So this is actually pointing out we got 10.18. This is the chi-square distribution with degrees of freedom 5. And what we found when we found the p-value was we found the area to the right of that line. And so that area was that small p-value. In that, if the chi-squared was bigger than 10.18, our p-value would be even smaller. For our ranges, this was about as small for our range method. This was about as small as the chi-square, about as big as the chi-square statistic could be, or about as small as the p-value could have been for us to fail to reject. If we, but want to also quickly talk about, again, I will always give enough table information for this to be done. But if I can get it up. Okay, there is in that same second distribution, we're basically always using the CDF. There is a chi-squared CDF. The lower will be your chi-square statistic. So that 10.18 in our case. Upper, infinity. So 1 E 99. And degrees of freedom were 5. Real fast, what was the range we had for our p-value? We had the p-value between two things. 0.1 and 0.05. So assuming I did this correctly. 0.07 is between 0.05 and 0.1. So the actual p-value was that 0.07. And so 0.07 is bigger than 0.05. We come to that same conclusion. Again, I'll always give enough on a table for you to do it without knowing this command, but if you want the actual p-value, you can use that chi-square CDF. But you do notice there, you need the degrees of freedom, and it doesn't calculate expected for you or anything like that. You need that chi-squared after you've done observed minus expected squared over expected, after you've calculated all of those and added them up. That's what got plugged in. But there's a way to get the actual p-value with a calculator. All right.
Dr. Mays,
Yes.
my calculator keeps having a domain error. Do you know what that means?
I can maybe look at your calculator and figure that out. I have some guesses, but would need to actually look at yours specifically. All right, so let's, in that last little bit of time, go back and look at that other example, start walking through it. The one skipped over. Random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differ from those people who have landline service, you can tell this is an old problem. The poll results may not represent the entire adult population. So what we care to know is whether people who only have cells, the majority of the population, versus the people who actually have landlines to be contacted. Again, old problem. Differ of whether those opinions of people differ. The Pew Research Center interviewed separate random samples of cell only and landline telephone users who were less than 30 years old. Here's what the Pew survey found about these people. Describe about how these people describe their political party affiliation. So we want to test this hypothesis. It's, once again, we have these, or in this case, we have two different separate populations. We have those that are landline versus those that have cell phone. So there's two different populations, and we want to see, are the distributions the same or are they different? The null hypothesis is the distributions are the same. The alternative is there is a difference. So first we want to find those expected counts. How would we find the expected counts for those that only have cell phones and claim they are Democrat or lean Democrat?
(49/96).
Not quite. There is a piece information there is a piece of information missing from our top table. And that is our row columns. Or our row totals. So how many total people claim to be Democrat?
Oh, 49 plus 47.
Yeah, so that is 96. How many people
42.
claim they don't lean either way? 42. Those that claim to be Republican, 62. And those, this is our N. So now we have all the information we would need. How would we find the expected for Democrat with only a cell phone?
49 over 96.
We are back to the situation where we have multiple rows in each and multiple columns. There is a formula for an expected. Now say we have actual 49, so 49 is not involved in our formula here. So expected is that we ignore the middle part of our table and we're using that other information of row times column totals all over n. So yes, 96 times 96 all over 200. 96 times 96 all over 200 should be 46.08. So landline. I'll copy those numbers down. How would I find the landline? Sorry, landline Democrat. Yeah. Row times column all over our total. Should get 49.92. I will refuse to lean with only cell phones is 42 times 96 all over 200, which is 20.16. And for the rest, I'm just going to fill in the numbers. 20.1.84, 29.76, and 32.24. Once we have that information, finding the chi-square statistic is for each one of these, we're going to take the observed, the actual information from the table that's printed, minus the expected squared. So for just the Democrat lean, I don't have it. I don't have that written down. Okay, for just the Democrat lean for the chi-squared, we would do 49 minus 46.08 squared over 46.08. That's just Democrat cell. And we would do that for all 6. So there'd be 6 more of these, or 5 more. And so I encourage you guys to find that, but what you should be able to get to is that the chi-square statistic is 3.219. Since we have multiple rows and columns, how would we find the degrees of freedom?
Rows minus 1.
Row minus 1 times column minus 1. How many rows?
33.
They can be different.
3 and 2.
3 and 2. We don't include the total. So 3, we have Democrat, refuse to lean, or Republican. And we have cell versus landline. So 3 and 2. So 3 minus 1 times 2 minus 1. Our degrees of freedom are 2. And I will leave the rest of that for you guys to practice looking up key values. Or finding key values with that information. As a practice for you all. All right. That is our chi-square statistic test. Thursday, we will get into chapter 10 with more on linear regression and some tests that come along with that. Have a great couple of days. See you Thursday.
That's your miss.
Hmm.
Think or not. I don't, I got any, what type of. I'm feeling, I have theories on. Yeah, I've had. I really need to do very work. Or the, yeah. I already have a lot of different.
We have 0.5 for your visual freedom. The visual freedom is that needs to be. Oh, no. So we have 5 degrees. Here. Is there something else? No, not yet. Yep.
There's some, two sizes.
I have unplugged that and possibly closed it, but you can check there for.
I got here a few minutes after you.
All right, thank you, Damien.
Yep.
Into